All right, so we're going to do one more 30-minute practice session. Or at least the video is going to be 30. You might have to take a little more time because you want to try to do the problems out. If you get hungry, I got a banana from the dining hall. You can have it later. I also got an apple. Trying to eat healthy, you know. Of course, I had the French fries. All right, mean value theorem for derivatives. We'll start there. So we have y equals x cubed. Oh, nice red marker. See if you can see that. Oh, yeah. Y equals x cubed. We're going to do from -1 to 3. Let's do -1 to 3. Let's see if we can find the value c. This is how it's stated in standardized tests. Can you find the value c that satisfies the conclusion of the mean value theorem? That sounded rather weighty. So what's the mean value theorem for derivatives? So really, you're talking about the average value equaling the instantaneous over an interval. So the average rate of change equaling an instantaneous rate of change at least once over a given interval, provided that the function's continuous and differentiable over -1 to 3. What's it mean, differentiable? It means that there are no cusps or no moments of discontinuity, no instances of discontinuity. I mean, I can't tell you what the slope is at that instant. 1 minute you're going up at +1, the next minute you're coming down at negative with no transition. There's no way numerically to figure out what happens there. I think in science they call that a jerk. Anyway, so you're right now trying to remember if you understand even what the question's asking. I'm going to talk about it. And you could also type into YouTube mean value theorem for derivatives and get all the practice you want. I'm going to ask you a question about the mean value theorem on every test. So you might as well get at it. So x cubed, that general shape, -1 cubed is -1. 3 cubed is 27. The average rate of change from there to there is 27 minus a -1. That's y2 minus y1. That's all I did. Over x2 minus x1. And we're going to set that equal to, well, we're trying to figure out where on this curve am I going up at that rate. It appears to be over here. Why do they in textbooks call it C? Because they generally refer to the left x value, the first one, as A. B on the right, since those letters are taken, I guess somebody decided to say C. So what is this C value? Well, obviously it's an x value, and that's what you're trying to find. How do you find instantaneous rate of change? You take a derivative. So the derivative of this is 3x squared. Looks like there's two answers here. The question is, are they both in this interval? Doubtful. The other place is probably over here that's going up at the same rate. Okay, so calculus is over. The rest of it is, can you solve it algebraically? 28 divided by 4 is 7. When does 3x squared equal 7? Well, you got to divide by 3. You got to take the plus minus square root. Well, minus the square root of 7/3 is to the left of -1, so we can ignore that one. It looks like the answer to this is C equals the square root of 7/3, which is less than the square root of 9/3. But it's certainly bigger. It's bigger than the square root of 4/3. Why did I say 4/3? That didn't help me much, did it? Well, I suppose. So square root of 3 is 1.73. Square root of 4/3 is 2 divided by root 3. That's too hard to do. Let's just say that I'm a little less than this number. So that would put me somewhere, and then I would be going up at that instant at a 7-to-1 clip. All right, there's another chance to look at the mean value theorem for derivatives. Maybe the second or third day that we've talked about it. I didn't like the way I pinned that video. I should have been talking to you like that. I will try to remember that going forward. I think I'll stay put. I've got all the problems I want you to practice right now on the board. That was the first one. All right, should be pretty good at the second one. Let me give you another cubic. Not only should you be able to do it, but hopefully understand what you're doing in line. So we're going to find the point of inflection. We're going to write the equation of the tangent line to the point of inflection of y equals, what did I give you this time? X cubed minus 18x squared, try to keep everything integer-like, plus 2x minus 3. Okay, should be able to look at this from local to end behavior, starting at -3, going up to 2 to 1. Pretty strong coefficient there, so it's probably going to look like that. We're trying to find this that coordinate first. That's the first thing we're going to do. We know this coordinate is 0, -3, and we know we're going up to 2 to 1 there. Up to 2 to 1. Okay. All right. So y prime, 3x squared minus 36x plus 2. Y double prime is going to tell us concavity, and that's 6x minus 36. Oh, boy, did I really give you something that large? Gotta do a new problem. I don't feel like putting 6 in there and doing that in my head. So I can challenge you right now by putting a 3 there. All right, doesn't change the fact that we're still going to get something that probably looks like that, although this is going to make it turn quicker. So we still got our 0, -3. We're still going up to 2 to 1. Looks like the point of inflection is right there. We're going to find that coordinate now. So we're still going to do the same thing. We're going to get y prime. But now I got 9x squared minus 18x plus 2. That's a whole lot easier to work with. So now we're going to do the y double prime, which is 18x minus 18. Good. I got a simpler number. So at 1, oh my God, this changes very quickly. Might even be here now. Let's see. We'll find out where it is, and then we'll redraw the graph. Okay, so let's find out where that point of inflection is. This is all I know so far. So at x equals 1, I get a change in concavity. What kind of change in concavity do I get? Well, let's graph 18x minus 18. Okay, so I'm going from negative to positive. So yes, concave down, which we kind of knew anyway. Concave down to concave up. So we put 1 in, and we get our 3. That should be minus 9 without looking. Oh, wait a minute. It's 3 times 1. Excuse me. Yeah, no, that's at 1. Yep. 3 minus 18. Excuse me. Now I've got a minus b over 3a. Did I make a mistake somewhere? 19x minus 18. So y double prime is equal to 18x minus 18. 9 to 36. I know I made a mistake somewhere. 36, that's one thing I want to highlight right now. When you do things from a different perspective and you get a different answer, that's how you find out if you made a careless error. That's hugely important. Hugely, because we're all going to make errors. We're human beings. We're going to make mistakes. Question is, can you find them? Now, if I had done the problem the same way I had done it originally, I might have still said 18 here. But because I was able to come from a different perspective, in this case, the geometry of completing the cube, minus b over 3a, which is actually the average of the roots of a cubic. Okay, it's all about the roots of a cubic or any polynomial that allows us to find some quick information. I was able to catch that mistake. So now I got to do this again. So this is 18x minus 36. So this thing changes at x equals 2. Okay, so at x equals 2, I put 2 in, 8, 24, I believe, but I got a little tired brain. 3 times 24 should get me minus 72. When I put 2 in here, you check and see if that's true. Plus 4 minus 3. So now we got double this, minus 48 plus 1. So negative 47. All right, so if that's negative 3, we can now complete the picture. Negative 47. So let me just start this again. Okay, so we got ourselves 0, -3, and we got 2, -47, and I need to know whether I'm increasing or decreasing and at what rate at x equals 2. So how am I going to find the rate at which this calculation is changing at x equals 2? Let me think. I'm trying to find a rate. There must be a mathematical operation in calculus that finds the slope of tan. Oh yeah, I'm going to take the first derivative and I'm going to work with it. And I am going to plug into the first derivative 2. And if I do that, I get 36. Without looking, this is going to be -72 when I put a 2 in, plus 2. Why? Because this was a cup shape, and if this is measuring slopes, at 2, I get a rate of change of the cubic, -36 plus 2, -34. And that's where I'm going down fastest. Everywhere else, this is increasing, then it's 0, going down faster and faster and faster until I get to this slope. And then starts to come back up again. Those velocities start to increase. So my velocities are decreasing until I get to this instant, and then increasing. So I guess I find points of inflection when velocities go from increasing to decreasing, or from velocities now, not the position, velocities, or from decreasing to increasing. So if I had a velocity graph like this, how many points of inflection does my original function have? 1, 2, 3, 4. I'd have 4 points of inflection. That's the first time you've heard that. Okay? You're going to hear it a lot more often. All right, so do we write the equation of the tangent line? It's right here. All the information you need is right there. So the tangent line equation would be -34. Grandma's heading south at 34 miles an hour. Go get her off the road. T minus 2, I'll work in terms of T. T minus 2, 2 hours from now, that's what she's doing. And where is she? She's down near Holyoke, 47 miles south of the border. Pretty close to Springfield, probably. All right, so that's that problem. I did not look at the clock. I will look at it now because I really don't want to do more than half an hour. When did I start? I feel like I've been talking about 7 minutes. All right, so we're going to say I started at 7 minutes after 1. I'm still here. All right, so I'm going to talk until about 1:37. All right, next problem we're going to do. The limit, let's do a quick one. What's the limit? As x goes to infinity of 2x plus 7 divided by x squared minus 8x plus 9. Okay? Hopefully you know how to do that from your last class. Anytime the denominator, let's just make a numerator of 10. Let's make the denominator 15. Okay? What's squaring going to do when I put bigger and bigger and bigger numbers in? It's going to make this go up faster than that. I'm eventually going up faster than that. Going up faster than that. Going up faster than that. What's that fraction heading to in terms of size? It's going to 0. So anytime the exponent in the denominator polynomial, denominator exponent, is bigger than the one in the numerator, fraction is going to go to 0. Okay? You can memorize the rule, but I'd much rather have you think about what's going on, because then you have true ownership. Okay. So that was a quick question. Every now and then we want to do a quick question. Like, for instance, we want to be able to do a quick question like 1 to 4 square root of x dx. And you want to have a picture in your head as to what it is. You have the chance to pause the video, think about the picture. Hey, the picture is this. 1 to 4. What's the area? Well, that's one strip of a rectangle right there. Square root of x is going to be the height, depending upon the x I give you. That's dx. I'll put it on this side. And what happens as I move to the right, the heights get a little bigger, heights get a little bigger, I add an infinite number of those rectangles, between 1 and 4. And that layering process we can do without a calculator. All right, so let's do it. You're doing it, so am I. So we're going to change this to x to the 1/2. Okay, so I know I have x to the 1/2 plus 1, which is x to the 3/2. If I add 1 to 1/2, and I'm dividing by 3/2, which means multiplying by 2/3, and I'm going from 1 to 4, and I'm looking at how the table changes. Grandma's position on Route 91 changes from hour 4 to hour 1. So I drop the 4 in. Square root of 4 is 2. 2 cubed is 8. 8 times 2 is 16 over 3. That's what I get if I drop 4 in there. If I drop 1 in there, I get 2/3. Looks like her position changed by 14 over 3, 4 and 2/3 miles. So in 3 hours, she has moved 4 and 2/3 miles. It's kind of crawling. I don't think she's even on a bike. I think she's walking. No, maybe that's the pace that I would set. Yeah, that's the pace I would set. So she's had a hip replacement too. I don't know if the arthritis is in the knees or not. I'm guessing it is. Anyway, let's move to the next problem. I think we should solve a differential equation. So Clarice asked, what's the list of things we need to learn? You need to connect with differential equations of the first order, which means easy ones to start out with. There's college courses based on differential equations. So I'm going to give you y prime, which is a rate, by the way. Let's do 4x plus 7. And I know that I have an initial condition of y1 equals 10. So that means an hour from now, Grandma is 10 miles north of the border, traveling at a speed, a velocity of 4x plus 10. 4x plus 7, excuse me. Been doing math since 8 this morning. 4x plus 7. Go ahead and do the problem. I'm just going to do it. Y prime is the same thing as saying dy dx. Anytime you work with an equation, you try to get your variables together, which means that the dx should come over to this side. Oh, that's starting to look like the stuff we kind of work with. How do I get little changes of y to morph into something else? I integrate. If I take a little change of y on top of a little change of y on top of a little change of y, I create the linear function y. Doesn't matter what letter I work with. If I integrate dx, I really have 1 times dx. Well, this comes from a linear function. That rate of change is constant. That's the function y equals x plus c. And it doesn't matter going up at 1 to 1. It doesn't matter which line. So that becomes y. And if I integrate on the left side, it's not equal unless I integrate on the right, which means that should have parentheses. So I'm measuring from 1. I know I have 10. So if I was going to measure 4x plus 7, which is something like this, and I started measuring from 1, whatever that area is to the right, I got to add 10 to it. Because 1 to 1, if I measure from 1 to 1, I don't get any area accumulation. Just adding a little layer of concept. All right, so let's just do the math. All right, this is an indefinite integral. If you integrate that, you get 2x squared plus 7x. And we also get c. Well, I know that y of 1 is equal to 10. Geez, I guess I can figure out when I put a 1 in, what I have to add to get to 10. So I put a 1 in and I get 2 plus 7 plus c equals 10. Sure looks like c is 1. That is the solution to Grandma's position function, which is what I asked you to do when I asked you to solve that equation. 2x squared plus 7x plus 1. Okay? All right. Let's see if you can write the equation line tangent to y equals the sine function. And x equals 3 pi over 4. Then you should be able to draw 1 period of the sine function, locate 3 pi over 4, put a tangent on there, and then see if your numerics make sense. I'm just going to do it. All right, you get to pause the video and try it yourself first. Sine function, right? So sine function, altitudes go up in the first 90, They go up in the first 90, then they come back down to 0, and then they become negative, bigger negative at 270, and then they come back to 0. Okay, where's 3 pi over 4? 3 pi over 4 is over here. So let's get a good little circle. 3 pi over 4. There's one chunk of 4. There's 2 chunks of 4. Oh, 3's right here. I got it. Woo! That's pretty bad, actually. Thought I had a good circle there. A little gap there. Got to work on that. Rotator cuff. All right, so now what do? We're at 3 pi over 4. We draw the triangle. We hopefully recognize that pi over 4 is a 45-degree triangle. 45-degree triangle. I hope you know the ratios. Root 2 over 2, negative root 2 over 2. Okay? So what is the derivative of sine function? Cosine function. Okay? What is the derivative of the cosine function? Negative sine function. What is the derivative of that? Minus cosine function. What's the derivative of minus cosine function? Positive sine function. What's the derivative of the sine function? Cosine function. What's the derivative of the cosine function? Minus sine function. What's the derivative of the minus sine function? Minus cosine function. What's the derivative? Hope I said all those right. There's a pattern. All right, so we got everything we need right here. So the equation of the tangent line is the slope at 3 pi over 4, which comes from the slope formula. Cosine of 3 pi over 4, negative root 2 over 2, x minus 3 pi over 4, plus root 2 over 2. This is linearization. That linearization is f prime of a, and a in this case is 3 pi over 4, x minus a plus f of a. That's what we're doing each and every time with different functions when we write a tangent line. We're taking the derivative at that x value. We're using subtraction to get rid of the x to convert it into the y. And then this is your second conversion, which is really changing your units. Slope, right? For instance, you have let's do the most famous slope, miles per hour. If you have change in hours here, well, what are hours morphing into? Miles. And that's really what's going on with a linear function. All right. Hopefully I had some success with that. Folks know what root 2 over 2 is as a decimal? If not, you gotta throw it in the calculator and find out. I'm not telling you. Yeah, I am. It's 0.71. You don't know those numbers, then you don't have a feel for what you're looking at. All right, so let's formal definition. I want to do a formal definition of the square root of x because I think you should see it. I'm not asking you to do this. You can just watch. So we're going to look at the limit as h goes to 0 of the square root of x plus h minus the square root of x all over h. Now I'm going to work with that. And the first thing I'm going to do is not write the next line. I'm going to work off of this, which is taboo in math, but my arm's tired doing a lot of math here. So we're going to conjugate this. Normally you conjugate things in the denominator. We're going to change the verb tense of this in the numerator. So what's the conjugate of that? Square root of x plus h plus the square root of x. And if I did that to the numerator, I got to do it to the denominator. So now we got some algebra. What's the square root of h? X plus h times the square root of x plus h. If you said x plus h, you'd be right. This is still the limit. Boy, are we going to work with this in a little while. Okay, what happens to the middle terms? Conjugates cancel the middle terms. And that gives me the square root of x. Negative root x times positive root x is simply minus x. What do I get in the denominator? Now, in the denominator, that's a little trickier. The denominator, I get h times the square root of x plus h plus h times the square root of x. Yes, that's what I get. So let's get rid of the x's. That's nice. And let's see. That's there, right? No, I don't need a parentheses there. So why did I put a parentheses here? Oh, I'm going to put the parentheses. That's what I wanted to do. Got myself in a little trouble there. All right, so I'm just going to leave it like that. So I didn't want to multiply this out. Tired brain, I did. Now I've corrected myself. So what can I do next? Now I can put h into h, and that goes as a 1. I can actually allow h to go to 0 now. Because if h goes to 0, woo, that's gone. It's going to 0. And what is the square root of x plus the square root of x? Now that I took the limit, it's 1 over 2 root x. And guess what the derivative of x to the 1/2 is? I'm going to rewrite this a little further over. The derivative of that is equal to 1 over 2 times x to the minus 1/2. And I wonder what another way to write that is. Oh yes, that's another way to write this. I am putting the square root of x in the denominator. Hopefully you see that from the work you've done in Algebra 2 and pre-calc. I don't know if you would have worked with this in Algebra 1 or not. I haven't taught Algebra 1 in so long. I don't know if students would be open to looking at that. I would hope so. Okay, so let's do a quick product rule. All right, 30-second question. Y equals the ln of x plus cosine. That's not product. Boy, brain's getting tired here. Cosine x. All right, you pausing the video. I'm just going to do it. So the product rule. Take the derivative of the first. Derivative of ln of x is 1 over x times the second, cosine x. You can leave it like that. Maybe a little dot here, I don't know. And then you add, but I know what the derivative of the cosine x is. The derivative of cosine is minus sine x. So I'm just going to do that immediately. And multiply that times the first one unchanged. Okay, and that's going to tell you the slope of this calculation at any instant. Let's look at just the mechanics of the following. Can you just mechanically do the following? 1 to x, 4t dt, plus 7. Would you please just do the mechanics of that? See where it goes. Curious minds want to know where it goes. Okay, you can pause the video. I'm not going to. 4t comes from 2t squared. Okay, that's the mechanics of that. I'm going to go from 1 to 4, and then I'm going to add 7. Now, why did I do it in that order? Well, the order of operations in math is you always do the hardest thing first, right? Now, I usually talk about that in my Algebra 1 and Algebra 2. I think I probably talked about it in pre-cal, but if I didn't, then you ought to hear it. All right, you ought to hear this little discussion. So mathematics started sometime in the past, thousands of years ago maybe. You know, what was the first mathematical thing that folks did? You think about it. You might have said addition and subtraction. I think it was more like, I kind of looked like a caveman. I think somebody might have been a male or a female. Females back then might have had beards too. I don't know. But, you know, I think somebody went, and then on a cave wall went, right? In other words, somebody had a thought about quantities. Then somebody probably started adding. Probably Roman numerals. I don't know. And eventually, you know, we got some other places that wrote different symbols. And then somebody probably went backwards. I went backwards once and put the wrong finger down during a upward bound family day. That was a little embarrassing. So I'll put the correct finger down. Got to be careful now. Subtraction. All right. And then what came after addition and subtraction? Multiplication and division. What came after multiplication and division? Probably roots and powers. Probably exponents and logs. Probably sinusoids. I don't know, but math has evolved, you know, integration, differentiation. Math has evolved intellectually. So how do you read a line? You don't read a line from left to right. So how would you evaluate 2x squared, 2x cubed plus 5? Well, you plug a number in, you cube it, you multiply, and then you add. Well, give that some critical thought. What's the hardest operation in this problem? Cubing. That's what we do first. So I'm sorry, please pardon your dear Aunt Sally can go out the window. It's not helping you understand integration and differentiation. Which do you do first? Well, they're inverse operations, so it doesn't matter. But you sure do those before you do addition. Right? So here's the hardest operation. I'm doing it. Oh, that was an X. That's the hardest operation. I'm doing it first. Okay, so now where do we go from there? Sorry about that. So where do we go from there? We drop X in. If we drop X in, we get 2x squared. And then we subtract. We drop 1 in, and that's 2. And then we add 7. So what was this answer? 2x squared plus 7. And that's probably as powerful a calculation as the history of mathematics may have seen, because something special just took place. I used integration to write a function. And there's an initial condition here. I don't know if you can spot it. Put a 1 in there. Tell me what you get. I didn't write minus 2 plus 7. Sorry. You can tell my brain's a little tired, right? There we go. Now we're there. Put a 1 in there. Tell me what you get. Oh, a 1 got me 7. Now, why is that true, and why can you see that? And I hope you can see it as you move forward. Because what if this was a 1? What if I put a 1 in here? How much area accrues under a curve from 1 to 1? Big fat 0. So a 1 gets me a 7. We have some knowledge. Okay? So why do I think it's one of the most important? Because you got a rate and an initial condition buried in that statement, which means that you can write a calculation based on rates. That's huge, especially if you're flying a spaceship somewhere. All right. Now I'm getting silly. What time is it? I got time for one more problem. Then I'll let you off the hook. What do I got? I got a ton of things here. Covered most of them. Let's go back to one. Let's go back to one that we talked about earlier. So let's talk about a velocity. Let's let our velocity be dy over dx. And let's make it x squared times x minus 3 to the cube times x plus 4. And I want to know how many points of inflection. How many points of inflection does that have? Told you how to do it about 20 minutes ago. That's long enough for you to forget everything I said 20 minutes ago. So let's revisit it. We're learning how to graph this in class. X squared, no sign change. Cubic sign change at 3. Cubic sign change at -4. Linear sign change there. So this is what the graph looks like. Put in a big number. We head into positive infinity. Cubic sign change, so I'll start that over here. Cubic sign change like that. Quadratic, linear. So that's what the graph looks like. So what are your velocities doing? Well, they're decreasing. Velocities are going down. So let's actually draw a velocity graph right now. These velocities are positive but decreasing. Positive but decreasing. Velocities positive means she's still going north, but slower and slower and slower. You know, right here, 1 mile an hour. Up here, she's going 10 miles an hour. Then what happens? Her velocity changes to 0, so that means she stopped, flat right here. And then what happens? She starts going faster and faster and faster in the southerly direction. This is when she's going fastest. These are still negative, but she's slowing down. So she's heading south, but slowing down. Oh, that does that. So what happened right here? What happened right? That's a point of inflection. When did it happen? It happened right there. That's where we had a point of inflection. Okay, I should have done this higher. Got a point of inflection right there. Okay, but she's still still heading south until what happens? She stops. But then what does she do? Heads south faster and faster again until we get right here. And that's the fastest she's heading south. Still heading south, velocities are negative, but slowing down. And then doing what? Heading north. So where are the points of inflection? There's one there, there's one there, and there's one there. There's three. So how do you count points of inflection from the first derivative? Happens at all the maxes and mins. That's what we just did. Now you may need to play that again. You're going to do it every day now. Going to try to, often as possible. When is grandma heading north? If I ask when's grandma heading, when her velocities are positive, which would have been negative infinity to -4. Those are all positive velocities. These are all positive velocities. And that was, I think, 3, right? Union 3 to infinity. All right, that's about a half an hour's worth of work. So I'm going to stop the video, and hopefully you got a little practice tonight. Definitely going to do the chain rule in the next video. And we may even, by that point in time, I got a lot of time on my hands today right now. So I'm trying to upload some videos. So getting a little, because I started this at 8 o'clock this morning and it's 1:40. So I'm at that stage where the old calculator running out of battery power. And so I think what I'm going to do is I'm just going to take a trip. I don't know. I think I've never been to Quebec. All right. I should be back by the morning. All right. We'll see you all.